right, it's my pleasure to welcome everyone to the last afternoon of our conference. And our first speaker is Professor Alejandra Castro of Cambridge, who will speak about the light we can see extracting black holes from weak Jacobi forms.
Thank you. Thank you for the invitation. I'm guessing many of you don't know me. So I'm in a math conference on arithmetic quantum field theory. My talk will have quantum field theory. There's going to be modular forms, but the reason why many of you don't know me is because I'm not a mathematician. I'm a physicist, I'm a theoretical physicist. So what's going to happen to you for the next hour is that I'm going to destroy all of the beautiful mathematics that many people in this room has worked really hard to make precise and elegant. And I'll just yeah. So don't cringe too much, okay? So that's basically, just bear with me. Because the nice thing, what I want to build a bridge, what I want to illustrate is how some of these mathematical objects enter in physics, and in particular in the physics of black holes. And who doesn't like a black hole, right? We're kind of we're at the BHI, so I feel also like it's kind of like the best between the middle. Like, so last year I was here for the BHI conference, and so now I'm here for the math. So okay, so let me give you that perspective, and yeah, please interrupt me. Like if I'm using too much physics jargon, or if things are not really very clear, just ask me questions, and I'll do my best to try to be as precise as I can. But in any case, let's get started. This is work that is going to appear very, very soon with these collaborators, Luisa Polo, Susana Ventaya, and Diego Vizca. Two of them PhD students, the last two, Susana and Diego, that are about to graduate, and I owe a lot to all of my collaborators there on the work that I'm going to tell you. So what I wanted to do is I'm coming from this physics side. Most likely what's going to happen during this talk is that I'm going to spend most of my time motivating what's going on, okay? Usually when I give Blackboard talks, what happens is that I end up just in the motivation, and then maybe I'll get to parts of point two. So yes, I will write what a weak Jacobi form is to some extent. But my guess is that I'll do a really mediocre job at telling you about symmetric product orbitals and exponential lifts, and I will have to wash through like this is my outlook. Okay, but just so you know, if we just end up in the motivation, I hope I just inspire you and give you some context about why we care about these objects in theoretical physics. So let's start then with the motivation. So something that is well known or a very famous aspect of black holes is that black holes carry an entropy. That's what the symbol S means, is the entropy of black holes, which a leading order depends on the area of the horizon of the black hole, the size of it, measured in what we call Planck units, divided by 4. So G here is Newton's constant. This is also known as the Bekenstein-Hawking area law, which is the leading part of a formula that receives as well corrections, okay? And so for the moment now, let me write this as ... Okay, so this is a famous formula in theoretical physics, a property of black holes that they carry entropy that is proportional to this area. Now, what I'm going to be doing, the rest of the things that I'm going to be saying during the seminar are going to basically be focused, because I see some physicists in the back and in the front. And so just to make clear that they know which type of black holes and which type of settings I had in mind, I'm going to be considering what we called BPS, or supersymmetric black holes. And this is just to specify that this area of the that I'm describing here is something that will depend on parameters of the black holes. And I'll basically think of them as something that depends on some electric charge that the black hole can have. And this charge is basically a mimicker. So the fact that I'm writing here Susie or BPS is that you can think of this charge with quotes as the mass of the solution. So it's something like how much mass the black hole has is basically something that dictates how big its horizon is. And I'm looking at configurations that are very special, where basically the mass is equal to the charge, okay? And in that context, so we have this formula from a gravitational point of view. But this formula, if you're just in gravity, if you're just doing general relativity, it's a bit confusing, okay? Because when I call this entropy, ideally what we want to say is that this equation should have been derived as basically the logarithm of some integer, of some number of microstates. Okay, that's what entropy means for the purposes of this talk. Okay, so this is basically an integer. It's what we usually call the number of microstates. Okay. But in gravity itself, we don't know what those microstates are. What are we counting? And the success of it, the cases where we have been able to establish that this actually comes from counting things is in the context of basically, so there's specific examples that come from either string theory or what we called alias CFT, where we have an understanding of like, this thing here, this black hole, these numbers that we compute from the gravitational side, if you include all of its corrections, will be the logarithm of an integer. Okay, so there's very specific control situations where we have that. Now, let me illustrate to you like how that goes. Okay, so how do we see that this number, like that this thing here can be understood as the logarithm of a number? So there's a famous example, and I'll illustrate it as a simple toy model. That was historically also how, in these contexts, it came about as an accounting for this formula. And so the toy model goes as follows. So let's define a function, tau, that I'll describe like this. So I'm defining that function, which will have coefficients dn, it's a sum over n. Here, tau is a complex variable. And what I'm going to, this function here, I'm going to assume that it has some symmetries. So I'm going to take the set to be a modular form, which for what I need for now, of course, a modular form is very understood to see, but what I basically need to specify is that this is a function as a function of tau that has this inversion symmetry. Okay. So an example in mathematics will be something like the eta-Dedekind function, like the DFNs there could be the number of partitions. I don't know, pick your favorite and modular form. Now, but by specifying basically this property, and here C, by the way, sorry, here C, it's just going to be, if I also impose, like this is invariant under shifts, this number C here, you can pick it to be a positive integer, 12 times a positive integer, okay? There's a meaning from the physics point of view, but for now, it's just a parameter that is going to be convenient for what goes. Okay. Now, something very famous about generating functionals of this form is a result by Hardy, Ramanujan, and Rademacher. Basically, that gives you, based on the symmetries, and basically based on this one, you don't need actually the rest of the modular group to say what I'm going to write. But basically, from here, you can very universally give an asymptotic behavior of what these numbers are. And the behavior of these numbers asymptotically in this notation that I'm using here is given by 2 pi c over 3 times the square root of n. Okay. In physics, we call this the Cardy formula. It's the Hardy-Ramanujan-Rademacher formula from the mathematics point of view. Okay, and so then you take the log of this number. And I'm going to get that this is 2 pi c over 3 times n plus corrections, of course. This is just the asymptotic behavior of this number for some large values. And where string theory or ADS CFT come in is that they tell you a way how you can relate these parameters that you have here into gravitational parameters. And so then the map to gravity is basically, it tells you that the central charge in relation to gravitational parameters, this number c, is 3L over 2G. In many cases, this is a specific version of the map, just it's a version that we usually use in the context of radius 3 to 2. So here L is a curvature radius of radius. G is, again, Newton's constant. And this number n is the mass of the black hole in units of the ADS radius. And if I translate it to the horizon size, it's basically, here am I going, I did it right? Yes. 3. So R plus here, so M is the mass of the black hole. Size of the horizon. And so then you plug this map into this formula here, and you're going to get 2 pi R plus divided by 4G. This thing on the top is the area, and then it will be corrections. Okay. So
C appears as a central charge in the CFT.
yes, exactly. So that's why I shifted here. So n. So from a CFT point of view, what I'm defining is a partition function. So what I would have said, so maybe let's just do a recap from the point of view of a CFT2. So in the language of a CFT2, tau will be an imaginary number times beta, where beta is the inverse temperature. And I would have written down that I'm computing the partition function and finding temperature as a sum over energy configurations, where I have a degeneracy for each energy configuration is weighted by a Boltzmann factor. And that minus C over 12 is the Casimir energy of the ground state. So then there's a ground state, which is vacuum state. That's energy times C over 12. And C is the central charge that defines the CFT. Okay. Very good. So that happened in 1997, roughly. It's a beautiful paper by Andy Strominger that basically showed how very universally you can reproduce the black hole entropy using these constants. Okay, that they all come motivated by this concept of alias 3CFT2. So now what has happened since 1997? Oh, okay, wow. So this was the state of the art in 97. So since then, there's two things that I want to, many things have happened, by the way, these are not the only two. But for the purposes of the talk and what I'm trying to motivate, there's been two developments that I find really interesting. The first one is that in computing the entropy, so this is the part that I was saying, I was regretting that I erased. So this came from an area law. Basically, in the language of quantum field theory, since this is a conference in quantum field theory, this means that this comes from a two-derivative Lagrangian that has basically gravity coupled to matter. Okay. And so that's why we call it like the leading correction in the semi-classical limit. But when you view this as coming from a path interval, let's say, so when you decide to quantize this theory, there will be corrections. And one thing that was really beautiful that happened in the year 2000s is that there's a class of corrections that depend, basically scale like the logarithm of the area in units of G Newton. And then there's going to be further corrections. And the thing that is quite beautiful about these corrections is that this, so here there's a number or a parameter that I'm going to call C. But this is a correction that you can compute basically from the gravitational path interval. And it's due to basically one loop determinants of massless fields. And so it's something that if you have specified your two-derivative theory, so if you specified classically which theory you have, there's a one-loop computation that you can do around that classical theory, and it will determine it will also give you a prediction on what the next correction is. Okay, so starting from like this classical point of view, there's actually two numbers that you can report on. You can report on like the 1/4, if you wish, which is very robust. And then you can also report on what is this coefficient here, okay? And this goes the work of Ashok Sen. Basically, he was the pioneer in this area and to compute these corrections. And he computed them from the gravitational point of view and also the matches, which I'll come through if I have the time to tell you how they were reproduced microscopically. Okay, so that's one development. So we've gotten better at quantifying dots there. So there's more universality, there's more information that you can get from the semi-classical theory that you might have thought. You don't need full string theory to know what some of the corrections are, which is nice. And then the second thing that happened is basically related to this formula here. So we had this, right? And all of you were very happy and excited with this. No one raised your hand, which is okay. But you should have, because one thing, when you match these things, you have to tell me, are you doing this in the right regime? And what do I mean by that? What is the validity of each of the derivations that I presented to you? So when I write an asymptotic formula, it's an approximation. This approximation that will be true. This is not the exact value of this. This is not an integer, clearly. It's exponential, like irrational number, so that we all know that I know that this is an integer. So how well am I approximating that integer? When should I trust that that integer looks like the exponential of a number? And so from the point of view of Cardy, Ramanujan, and the Rademacher expansion. In this language that I'm describing it right now, this is a formula that is valid. It's really, really good. It's a really good approximation if n is much bigger than c. Okay? You can, of course, correct it and you can get an exact formula, but if I only write the exponential for you and I stay there, then this is my limitation. Okay, so this integer n has to be much bigger than whatever central charge you had. Okay, so if the value of c is low, then the approximation is better and better. But if c starts growing, then it's worse. Okay, so this is from the number theory point of view, they're mathematics, like that's the validity. This is important, okay, so that we keep in mind that we're in this regime. Now, from the gravitational perspective, I'm writing this formula. I'm writing A over 4G, and how I've been emphasizing here, this is a two-derivative computation, and you're like, that all sounds really good, but that also comes, like when I write dots there, I'm also assuming that I'm leaving something behind, that there's something tiny, and I need to tell you what is that tiny thing, right? And so from the gravitational perspective, I trust this. So if you just look at this as face value, the basic requirement, this is an expansion in the size of the black hole in G Newton, which is very big, okay? Much, much bigger than 1. That's what, that's when we write those equations in physics, that's what we mean. Now, in the language of like the dictionary that I put there for this very specific instance, basically, there's two things that I mean here. So I basically mean that R is much, much bigger than G. The size of the black hole is much bigger than G. And also what's important in the gravitational point of view, I introduced the curvature radius L. L also is much, much bigger than G. Okay, that's what semi-classical gravity means. Okay, so the radius of curvature is much bigger than the Planck length. The size of the black hole is also large in Planck units. Now, if I translate this to gravity, this will basically tell me, so I will use the equations that I have there, and this will tell me, this approximation would imply that R plus is much, much bigger than L. That's not the same as these equations. Okay, this is what we will call a really, really large black hole. But the thing is that this can also be true. So these two things combined tell me that I should also trust this formula if R plus is of the order of them. There's nothing wrong with these computations. This result is robust, even if I'm in this regime. But clearly here, then I get nervous if I take n to be very close to the central charge. And so that came to the second development of what are the counting formulas that actually allow me to trust this expression in this parameter space, right? So now we need to have a refinement of which partition functions we're going to look at. So basically, which of these set of tau allow for this dn of n to grow exponentially for basically, so in the translation that I'm doing here, so if I write it in this language, I basically want n to be comparable to c, but then now these two parameters to be big. And this was answered. It's a paper by Hartman, Keller, and Stoika. It was answered, I forgot now which year the paper, it's also from after 1997. Let's guess, 2015 or something, no, maybe 2012, I don't know, it doesn't matter. Okay, after 2010, this paper was written, and they basically found a criteria for when this applies. So they put a restriction on these coefficients. So this has an answer. And it goes under the name of what we call nowadays, so Hartmann-Keller-Stoica bound. And the answer to this is that you will be able to use this approximation in this regime when, so the condition is basically, so let me just write this as star. So star is true if on the lower part of the spectrum, you're bounded basically by an exponential. Okay, so these are the configurations here. These configurations is what we're going to call the light configurations. Because they're basically configurations from this point of view that if I measure the energy relative to vacuum energy, like basically it's cases where the total coefficient here is negative. Okay, so that's why we call them light. So when you get something up here that is positive or bigger, then we call them heavy. And then the guys that have negative numbers in here, we call them light. Okay, and when I get to weak Jacobi forms, I'll make a distinction between polar and non-polar states. But in this language where I just have one variable, it's basically states of this form. So it's basically saying in the lower part of the partitions, if your coefficients are bounded by an exponential, then you can apply this formula in this way. Where this parameter C here, it's important, I'm always taking it to be large. Okay, actually strictly infinite. But that was a second result that I wanted to highlight. Now, from a mathematic point of view, and again, I'm going to stress this, the thing that is interesting, and I want to perhaps motivate the audience, notice that usually from the mathematics, when you try to extract these coefficients, this parameter C here, it's just fixed. What physics is like what black holes are telling you is like, don't fix it. Treat it in the same footing as you're treating the other variables, which is a little bit awkward because you like to not do that. You usually say, no, this is just like, okay, just tell me what that value is, and then I'll tell you all about the form. No, gravity wants to coarse grain it. Gravity wants to make it a continuous parameter. And so then that's part of the difficulty in understanding what are the conditions and criteria when you treat it in that way. And okay, so we have these two developments here. So we have 1 and 2. And the thing that I wanted to understand.
Sorry.
Yes.
Does that mean we should be studying families of modular forms depending on C?
Yes, and that's where this is an example of families of modular forms. So that's where in point number 3, I know how to describe families of modular forms in a systematic way. It's not the most general family, but I love them because it allows me to be very precise about what it means to treat this as a continuous parameter. So in the same way that here, what does the generating function do for you? It's basically allowing you to treat n in a continuous way. And so then I need to also then think of C as like, oh, can I add another variable in there? And then also treat it in a similar footing as how I'm treating n. And the exponential lifts are basically, or if you know of Siegel modular forms, these are examples of cases where you're treating this extra parameter in this way. But it's not a common thing. So that's this is my frustration. I would like to know more cases than the ones that I have here. So here I have a lot of control. I know exactly what's going on. I can tell you everything, but we need more because gravity is way more robust than these specific examples. So okay, so the thing that I wanted to then understand in combination, so this is a development from the perspective of ADS-CFT. This is a development that came from more the gravitational path integral. And I wanted to understand then what is the fusion in a sense between these two developments? So the main objective, the thing that I wanted to understand is basically how this number C here is predicted or controlled by the data that I have in this light spectrum. So what is the relationship basically between these two things? So if I give you the light spectrum, and so that I know that I am within this HKS bound, then what do I learn about this logarithmic condition? Is it something that it's a consistency condition? Is it dictated by symmetries? Is it like a boring thing to have computed? Is it controlled by just modular invariance? Or did I really needed to know something about like the specific generating function? Because this part here didn't teach me anything about, like, this is great, but it's also awful. From the point of view of quantum gravity, like it's great because it's like very robust in the same way that this one was very robust, but I didn't learn anything about like which modular form I was doing, was any. This, yeah. So I now want to know what makes this like microscopic, and so the next question is like, look at the next correction. So how do you tie, how can you see that you're really having this microscopic description? So, okay, so with that, the context in which I do these computations, so ideally, one would want to do it in general, but that's difficult. So what we're going to do, moving on to the second point, the classes of forms now that we're going to consider are this weak Jacobi forms, okay? So this is where we're going to be asking this question. And that's why at the beginning, I said that I was looking at BTS supersymmetric solutions, because when the counting formula is a weak Jacobi form, it's usually associated to an elliptic genus, an index. Again, if these words don't mean anything to you, don't worry, it's fine. But I can tell you more afterwards about why this is a limitation. Okay, so point number 2 now. In order to answer this question of what the relationship is between these two things, let's look at weak Jacobi forms, okay? So these are forms now that basically go from the upper half plane times the complex to the complex, meaning now I'm going to have two variables, tau and set. So tau is in the upper half plane, set is the complex variable. What makes these objects weak is because one of the integers is going to be restricted to be positive. The other one is over all the integers. So this is how I'm going to think of them in terms of a generating functional. And the words weak Jacobi form basically mean that this function phi is modular in tau and basically elliptic in such. I think I'm not going to write all of the equations. No, I do need to say something. Sorry. Okay, so I'll write one thing. One of the transformation properties, I'm not going to write the elliptic one, but maybe let's just write down the modular transformation. Just to introduce. So that's a modular property in its full glory of these type of forms. And the reason why I wrote this equation is because I just wanted to characterize two properties of this form, which is their weight and their index that I'm calling T. Okay. Now, these properties, like the combination of the modular and the elliptic property of these functions, so the elliptic one is just a shift, symmetry, and set. Basically tells me that these coefficients here, I'm writing them as a function of two parameters, N and L. But you actually can reorganize this in terms of its discriminant. So this D of N and L is convenient to think of it in terms of delta, which I'll write as N minus L squared over 14. And also, of course, they don't just depend on the discriminant, they also depend on N L times mod 2T. But this allows me to differentiate between two classes of states. So the two classes of states that I'll have are basically cases where delta is negative. So these we will call polar states. And cases where delta is positive. Or non-polar states. And then the other characteristic of these weak Jacobi forms is that there's going to be one state that I'll call delta 0, and I'll write it as minus b squared over 14. This will be the maximal. These forms also have a maximal polarity, and I'll characterize it in that way. Okay, where b is an integer. And well, in absolute values, perhaps b is less or equal than t. Okay, so these are the types of forms that I'll have in mind. Maybe in relationship to the old notation that I was using, I can write it here. So if I translate what I wrote here for the weak Jacobi forms, delta 0 usually is something like minus c over 12. And well, delta is n in the simple case. And then this bound is basically the statement, the nicer way how to write it, this bound here, is that it's a restriction on the polar states. Okay. You could actually say, sorry, it's minus c over 12. I think, yes, that's how I want to write it. Okay. Very good.
So partition functions of CFT come naturally disappear like one point function, or is there something in the physics that naturally tells you to?
It's a gravitational path integral, if you want. Like, yeah, how would I think of
This extra dependence on a point on the curve, on the elliptic curve, something that.
It will be so in the context, for instance, the simplest case to describe again is this case of ADS3. So it will be data of the so tau, let me think of it as the complex structure on the torus. That basically is fixing some data at the, so I'll have a manifold like ADS, let me think of it, something like this. And so at the boundary of the manifold, I will have, well, a solid torus, and tau is basically telling me something about how I'm fixing periodicities at the boundary of that torus. So when I say, ideally, we want to say that the set of tau is some path integral over metrics. Here, basically, what we will write is that at the boundary, the metric or the topology at the boundary is basically that of T2. That's how it gets encoded. So you're summing over all configurations that have the same torus at the boundary. Yeah, in more general cases, you would just say you sum over all manifolds that have a periodic direction that you identify with the periodicity of Euclidean time, which is theta, and related to time.
If you can actually get a Jacobi form from like inserting the observable.
I will-
endpoints.
Well, this side is really difficult to compute. People have tried. There's hints of this. So and basically they come because of this leading behavior and other aspects, but there's only one case where an honest to God computation of this side actually gave a Jacobi form on this other side, but it required tons of supersymmetry. It's like yeah, it's N=8 supergravity, supersymmetric black holes in it. It's this one case where exactly like, and you get like the exact Jacobi form on this side, but it's like, yeah. General, we have like there's a lot of hints that we get the right structure, and but overall we don't. Okay. So let me see. Okay, so now, so this is the type of objects that we want to study. And so then the next thing that you would maybe say to me is like, okay, but Alejandra, you know about Rademacher, so we know exactly how these coefficients behave. So why don't you just like, why are we doing this like kind of cheap tricks? It's like use the Rademacher formula and learn everything that you need to know. That's an exact formula. It's beautiful. I love it. It's great. But the problem with it, maybe let me just write pieces of that formula. So this is where I get nervous with this formula. We will use it as a diagnostic, but so from the point of view of Rademacher, will tell me, okay, grab any module of any of these weak Jacobi forms that you want. Well, there's some restrictions on the weight that I have to be careful about, but okay. Here I'm going to write a formula or parts of it. So let me just think that the weight, which I called K, right? Yes. Let me just put the weight equal to 0. There's of course formulas for this when the weight is not 0. Basically what Rademacher tells you is that when you want to compute one of these coefficients, and in particular, if this is a polar state, sorry, a non-polar state, so this will be a configuration that has delta positive. It's basically controlled by the polar coefficients that you have in this way of this thing. It's a long formula, so I'm not going to, I'll write some dots at some point. And then there's a sum over here over C. I'm basically writing the whole thing. And it's a Bessel function, and okay, the Kloosterman sum. Okay. I don't know. But okay, there's an exact formula. You guys have derived an exact formula. This is great. And so you tell me, okay, we're done. Right? Just like tell me where gravity comes out of here. And so basically, this is something that tells you, oh, if you want to know something about a non-polar state, then this sum is over non-polar states, and then you need to know that this is the only part of the formula that you don't know. So it just relates heavy to light. Okay. And this leading exponential behavior that I erase is basically the first term in this Bessel function that gives you that exponential growth here. Now, this delta 0, so the issue that I have right now is that in many cases actually B is equal to T. So this delta 0, so I was saying to you, this delta 0 is basically, in simple examples, is this minus C over 12. And basically something that is controlled by the index. So if I put that B is T, which is the biggest value that we can have, this is basically minus T. But this is the parameter. Remember that C, I want it to be very, very big. Okay, and the thing that I get nervous about this formula, maybe I'm just a dummy and one of you will tell me get over it, which is fine, it's great. I would love to hear that. Is that it affects the ranges of the integral. So I don't know very well, like I personally get nervous if I have to take continuous versions of things that affect the ranges of integrals. I cheat a lot when I do integrals and do sums, but this is one of the things that I don't feel comfortable with. I don't like manipulating this as a continuous variable because it's a range of a summation. Okay, so I don't know how to deal with that. But I want to estimate and basically understand what happens to these coefficients if I impose this HKS bound. Basically, I want to see what would happen to these coefficients and its correction. So I know that I'm going to get the exponential growth. That's fine. That's why I have the Bessel function there. But I want to know how the subleading corrections are going to behave. And for that, I need to understand how do I manipulate the parts of the sum. And that's where we're like, maybe we should write a paper or think about this. Okay. So the first method that I'll just tell you the result because I'm actually, I have like 12 minutes left. So I won't be able to tell you how we did it, but basically the first way that I approached this was by saying, okay, let's do a worse job than Rademacher. So he used the full modular group. So he used all of these transformations and defined this contour in terms of those beautiful circles and basically using the full strength of the modular group, he came about, this is the exact coefficient. As a mediocre physicist, I'll only use one of these transformations. Okay, so I'll use the version of what I was writing before of the tau going to -1/tau. Okay, so I'll just use the S transform of this transformation and try to estimate the coefficients. It's a bad approximation for most, like I'm not going to be able to reproduce that if I just use one element. But this is basically, it will be a useful way how to write the formulae. So that means in our terminology, when the paper comes out, is that we're going to be using, what I'm trying to convey with this, is that we're going to be using what's called crossing kernels. Okay, so when I think of that form, so the way that this gets implemented is that instead of thinking of that as a discrete sum, I'm going to think of it in terms of intervals, and I'm going to define a distribution. And then the rest of the stuff goes in here. Okay, so if I wanted to reproduce exactly the Jacobi form, then these are delta functions, so that's why I'm calling them distributions. But basically, this is going to give me a way on how to coarse grain the system. Okay. It's not explicitly coarse grading the index, so it's not doing this, but at least it gives me a little bit of like, I know that I'm not going to get exact sums as results, I'm going to get integrals. And so with this perspective, what we basically showed, the version of Rademacher that we showed, was that that formula there, in terms of this distribution, looks like when you look at the heavy part of the distribution, so the states that will have a positive discriminant, you can write it as an integral. I'm probably writing too low now in the board. In terms of the light part of the distribution, times a crossing kernel. P, and what I'll say about P, we have an exact expression for it. Let me just write it. So this P here, it also has like a Bessel function. It has a bunch of stuff, but maybe let me just highlight the important bits. So it has the index there. It has that same delta over delta prime, but then the Bessel function here Because of, yeah, you have to regularize some contours in a different way. You get -3/2 instead of +3/2, which is an indication that this is not, it's just an approximation to the numbers, not an exact one. You don't see the Kloosterman sum, that all gets washed away, and then there's a step function for delta positive. Okay, so this is the worst job, a worser, sorry, not the worst. You can do worse than this. I do have standards. This is like some middle way through of like how to do it. But the nice thing about this expression then is that here is where I can see how I implement the HKS bound. Because then I can model in as a function what the light states are doing, and then what are the important pieces that come in as a correction. In contrast to this other formula that gives me less control. And so what we noticed then, the outcome was twofold. So we noticed that there was what we call the universal regime, where delta just needed to be slightly above delta 0, the absolute value of it, these two numbers being big. And what we could show is that these coefficients now, we also show that this is a good approximation for D, so that's why I'm going to write D now. But basically up to an overall number, what we showed was that this coefficient here, I'll define for you in a moment what these symbols are. We showed that a good approximation for these numbers was this, where this row 0 of delta 0 is accommodating for the fact that you can have for the maximal polarity state, so for the state that has L equal to -b, you could have a non-trivial ground state degeneracy. So this number doesn't have to be necessarily 1. So this is basically a ground state degeneracy. It shows up in the explicit examples from string theory, so that's why it's important to have it there. But in some previous papers, people put this number equal to 1, but it is actually there. Now, we call it universal because if you're looking at configurations that are in this regime here, actually, the only thing that you needed to know about row light was that it satisfied the HKS bound. That formula that doesn't have any sensitivity to what this thing is, but you do have to be mindful that there's a non-trivial ground state degeneracy. And in these examples that were successfully described, this number is non-zero. So it's important to match it to the black hole. So all of these things that I'm basically describing here, when you take the logarithm of this is what's going to give you this logarithmic correction that I was describing for the black hole. Now there's another regime that we call a non-universal regime. Where you can take the opposite. It's a little bit awkward, but actually there are black holes for which this is relevant. It's not the example that I gave you, but there are cases where you're in this kind of strange situation. And with these same methods, you can also describe this DNL. It also will be controlled by some ground state degeneracy here. But in this case, there's a bunch of stuff that shows up. Where basically this parameter, so I'm introducing here two new parameters, W and alpha, that show up there. And this is data in the light spectrum. So where alpha is a number between 0 and 1, so it's within HKS. Gamma is a positive number, and W here is some polynomial extra part. So this is just to illustrate that, for instance, if you try to explore what happens to the coefficients in a regime like this one, you can still extract information. You will still have like an exponential growth of the states, but then you do have a lot of sensitivity to what this light spectrum is. Unfortunately, I don't know how to get this from that. So this is where, like, I don't see it, but it's a true statement. Now, since I have 3 minutes left, maybe instead of talking about symmetric product orbifolds, I can tell you when these two cases are relevant for black hole physics, because we all love black holes, right? As we established from the beginning of this seminar. So just so you know, so if you look at this type of regimes, so there's two cases that accommodate this. So one of them is the example. So I gave you this example of ADS3 CFT2. This was like my working example. The name of the black hole here is called BT set for the name of the authors. So, but then there's another black hole, another supersymmetric black hole, for which this is the relevant regime. And it's basically a black hole in n equal 4 supergravity and d equal to 4 dimensions. It's a quarter BPS. And basically it's characterized by, it has electric charges and magnetic charges, fancy, we call that a dionic configuration. This is a black hole that when you translate the data to the data of the CFT, basically this delta 0 is something that goes like minus q squared. N is basically something that goes like p squared, and L is q dot p. And so what you can see from these formulas, just because of how I'm writing it, you can see that basically this is a case where delta is comparable to delta 0, just because q squared and p squared are things of the same order from a gravitational perspective. So this is a case where you have basically this universal regime. So when you match this, so you do a computation in gravity, you compute your logarithmic correction in gravity. This is dictated by the massless field. From the point of view of the CFT, the only thing that you needed to know was the ground state degeneracy in the remote sector. That's what you achieved the match. Okay, so that's what's going on when we say that those two numbers were matched. Now, this other regime, there's two situations where you have this type of scaling. Maybe let's do different color. So for the non-universal regime, you will have, the first example is also n equal 4. But now if you go up to 5 dimensions, this is called the BMPB black hole. It's a fancier version of the Strömmen-Jourvasa black hole where you have, well, because of string theory, they're called Q1, Q5, and N, but you basically have 3 electric charges. These are the number of D1 branes and D5, doesn't matter. You have 3 electric charges, and you also have an angular momentum, J. And in the language of what I'm describing here, basically delta 0 goes like minus Q1, Q5, N is N, and so that's also why the notation, so it's momentum along one of the directions, and L is basically J. And so here you can see, that's why I'm calling this in this other hierarchy. In gravity, all these charges scale the same way. So delta 0 goes like charge squared, but delta will just go like 1 power of the charge. So this is a case where delta 0, the absolute value of it, is much bigger than delta. Now, the thing that is interesting here, what I'm illustrating in this formula, that if you want to compute this microscopically, which it was done, you need all this information about what the light spectrum is doing. When you do the gravitational computation, it's the most boring computation in life. It's dictated by symmetries. It's what we call zero modes. So the fact that these two things matched, it's like highly non-trivial. Because this is actually dynamical data. It's like spectrum data of the CFT. And from the gravitational point of view, you were just counting how many killing vectors the thing had. And it didn't matter how much matter fields you had and stuff. It's a really interesting case. And then the last case, here, there's another case that goes back to 4 dimensions. It's black holes in n equals 4, d equals to 4. It's described in terms, if you want the string theory setup, is I like to describe it as 3 magnetic charges, or sorry, some set of magnetic charges, Qi, 1 electric charge Q0. This you can think in terms of the 4 branes, this in terms of the 0. The OSV formula, topological strings, is supposed to say something about this. But the thing in this case is that this is also a case where you're in this non-universal regime, because delta 0 goes like p cubed, and delta just goes like q0. So when you see how the variables are mapped and people try to account this microscopically, here you're also in a case where you're not in like the usual, you're very far from what you would have called the usual Cardy regime or asymptotic regime. Okay. So yeah, I didn't have time to talk about symmetric product overfolds or exponential lifts, but if you're doubtful of these expressions, what we also did in that context using those forms, there's different methods how you can get similar answers, and we just contrasted all this like mediocre work that I did here using crossing kernels. You have other methods to extract formulas there, and you can see that they exactly match this form. So, and then those are also relevant counting formulas for some of the examples that I'm presenting here. And so it kind of gives us a nice perspective on the problem from different angles. But basically, yeah, how do you read a black hole from a weak Jacobi form? You first find the exponential, and then tell me how the corrections go. This is the black hole, and then this is its correction. So yeah, that's, I think I'll just finish, I'm over time, so thank you.
Thank you for a talk with massive content. Are there any questions?
Yeah.
All these examples of different dimensional black holes, I'm confused about the relationship in modular forms. Are you always seeing a 2-dimensional CFT at the boundary, or is it different dimensional CFTs? And
No, so all of these examples, one thing that they share in common is that even though sometimes you don't have explicitly this, there's a reason why, even though I'm in a different number of dimensions, we expect to have a CFT2 underneath it. Why a modular form is the right object. And that usually comes, it's a more complicated part of the story, but okay, so the thing that definitely all of these examples share is that there's an ADS2, not quite ADS3, but they share an ADS2. And in the framework of string theory, this ADS2, you can have like uplifted it to an ADS3, and then that motivates why you have a weak Jacobi form. Now, there's many black holes for which the counting formula that is relevant is not a modular form. But in some sense, so there's two things that here I would like to describe. The first one is that if you wanted to use a weak Jacobi, let's say that you did not know about ADS352, right? So you were born before the revolution, and but you knew about black holes, and you knew how to do a gravitational path integral, and you're like, let me try to see if there's a counting formula that reproduces these numbers. So you would have maybe gone through the Harvard-Ramanujan thing and noticed like, oh, maybe I have to relate things like this and that. What I'm saying is that if you insist of using a modular form, that modular form will also tell you things about its corrections. And so then you would have a different consistency check of like, can these numbers here also accommodate the corrections? Because the gravitational path integral will also make a prediction for you on that. And so for instance, there are black holes. So for instance, in this theory, and also in this theory, These are the BPS black holes, but for instance, there's a non-BPS black hole in this theory. So this is just to illustrate why I would say, here's an example where even though I'm in the same theory here, the counting formula is not a modular form. So in this theory, there's also a black hole that is non-BPS. In the language of these string constructions is built out of this here with the 6 brains. I compute its entropy. So I get A over 4. We computed its log corrections here. And these, so we got a coefficient here times log A over G. This number here depended on the ratio of, if you wanted to identify an N, or let me write in gravitational language, it depended on the ratio of Q over P. So it looked like a ratio of Q over P times the log of the area. Q over P, roughly speaking, it maps to deltas and delta knots, right? So if I get here something that has dependence of delta times delta naught in front of the log, it means that I should have gotten formulas here that look like the power to delta over delta naught. They're all integer powers. So this black hole here, I can assure you, this does not come from a modular form. The area law, if you want, you can always play this game of like, how do I identify these things with black hole parameters? There's an exponential number, you'll get it right. But this part, you're not going to get it right. This is a prediction from the gravitational point of view. What we're illustrating here, the corrections are also, they're limited on how they can be based on the properties of the counting formula. And there's cases where you're not going to be able to match it. So that's a way how you can learn about what is the statistical nature. That's why I find these corrections interesting, because it will teach us in more detail. Like, so you start from something very coarse. It's like, let's try to decode the microscopics. And this is where the microscopics come. So definitely in principle, we should be able to signal these things. It's like, this is not coming from this type of counting formula. But yeah, so we need to do more homework. That's why one of the things that I would like to know is basically, yeah, from the statistical point of view, from like the number theoretical point of view, what are possible coefficients that I can get here so I can bootstrap the system so that I can like really put constraints on both sides.
Are there further questions? All right, let's thank Alejandra again.